Hello everyone! We are starting a free open lecture on our Discord. If you are a viewer and want to ask questions and get answers in an online format, join our lectures. You can find the link to Discord in our Telegram channel. Today we will talk about bubble sort. I don't think there's much to say here. It's one of the classic sorting algorithms, but unlike the others, it has a very strong distinction in terms of stability. You will learn more about this towards the end of the video. So the definition? Bubble sort. Sorting by simple exchanges. Its second name can be called. This is because it works as stably as sorting by simple exchanges, but it has slight differences in terms of swapping and indexing. But for the most part, these sorts are the same in terms of speed and almost identical in their working algorithm. So it can be said that these sorts are interchangeable. The sorting algorithm traverses the array from start to finish, swapping unsorted neighboring elements along the way. If we are sorting in ascending order in this case, we actually want the second element, which comes later, to be greater than the previous one. Accordingly, we swap all pairs so that the second element is greater than the previous one. Basically, there's not much more to say here. Purpose. In computer science, we use programming to sort data. The purpose here is classic, just like with all sorting algorithms. After all, the goal of sorting is to sort the array, no matter how absurd that may seem. A step-by-step algorithm means we will take exactly the same array as in the previous examples, and we will have n8, which is the size of the array itself, and the array R65118714. In this case, we will consider a slightly different array. Yes, this is already a semi-replaced one that will have answers. We will see later why this is needed. The array itself will be exactly the same as in the previous lectures, 65318724, and our goal, accordingly, is to have all the elements in order, 1, 2, 3, 4, 5, 6, 7, 8. So, the array should ultimately look like this. So, what happens here is we have an index that starts from the first index. Well, you can start from the 0 index, but when it's the 0 index, it doesn't have a previous element to swap with. In this case, the algorithm will be considered with the replacement of the previous element, not the next one, because there are several variations, and I will show several codes later. Accordingly, we will initially set it to 5, and we swap it with the previous one. That is, if 6 and 5, in this case 6 is greater than 5, it stands before it, so we swap them. Accordingly, here you can see that 5 and 6 are already in place. We do the same with 3 and 6, that is, obviously 3 is less than 6, so we swap them. Therefore 3 will be here and 6 will be here. The same with 1 and 6, we swap them out. And then we encounter 6 and 8. Obviously 8 is greater than 6, so we won't swap them. Next we look at 8 and 7. Obviously 7 is less than 8, so we swap 8 and 7, and 8 moves later. Next, 2 and 8, the same thing. 8 moves forward and swaps with 2. The same thing, 8 moves forward and swaps with 4. And thus we get the array. 5, 3, 1, 6, 7, 2, 4, 8. 8 has moved to its correct position. We understand that this is the maximum element in our array. Therefore, next time we will not go all the way to the end of the array, and, roughly speaking, this barrier that you observed while I was talking about all the swaps within this array, it moves back by 1 unit. Therefore, there's no point in touching the last element because it will already be the maximum element.
Want to become a great programmer? Subscribe to our Telegram channel.
In fact, we do the same thing with the next iteration. That is, we actually also set the index I to 1, and I1 will be at 3. And we go through it in the same way, but up to the second to last element. This way, our array becomes 1, 3, 5, 2, 6, 4. And the 7 has moved to the second to last position. The barrier has shifted by 1 unit. Accordingly, we will do the same. Place it here and here. There they go. Swapping again. And in the end, we see that the 6 is in place, and again the barrier has moved. And so on and so on. That is, the 5 will be in place, then the 4. But here, regardless of the sorting methods that will take place, we understand that in this case the algorithm will not be completed because this sorting method does not check if the entire array is already sorted or not. We will not have such a check. Therefore, in this case, the sorting will occur in cycles, meaning there will be cycles 1, 2, 3, 4, and so on, 5, 6, 7, until all elements are in their correct places. Obviously except for the first element, which will automatically move to its correct place. Thus, the algorithm's complexity is O(n) squared in both the best and worst cases, unlike a previous sorting method. You can watch a video about the previous sorting method on our channel. It had a best case complexity of O(n) and a worst case complexity of O(n) squared. This was because it checked if the previous element was greater or smaller, and if it was already smaller, it did not proceed with sorting. Accordingly, the best case was when the array was already sorted. In this way, we went through all the elements, roughly speaking, checked if the previous element was less than ours, and thus we didn't need to sort anything further. Therefore, it had a better complexity of on. In this case, the sorting works consistently at on squared. Also, there is a video on our Telegram channel about asymptotic complexity and its calculations, explaining how it works. There is even a bit of mathematics about asymptotic complexities. Accordingly, let's move on to the pseudocode. We have a function, which is also called bubble sort. The data and the number of data items are passed there. They can be passed in reverse order. The number of data items first, then the data itself. Accordingly, we have an index I that goes from 0 to the number of data minus 1, meaning it goes to the very end. And we have an index G that ranges from 0 to the number of data minus I minus 2. This is specifically designed to determine the barrier, meaning when I is 0 we go to the end. There is no point in taking them because there will be swaps anyway. In this case, the swaps are moving forward, not backward, as explained in the algorithm. Here you can see these backward swaps, just as we wrote. The sorting data works the same way, meaning if you want to swap forward or swap backward, you just change the references between each other, and basically nothing else changes. The algorithm will work exactly the same. Accordingly, if our data at index j is greater than the data at index j plus 1, meaning the current element is greater than the next one, we swap them. After such a cycle of sorts, roughly speaking, the algorithm will be completed. Just as we did here with this code, we return the data, and this data will be sorted in ascending order. Accordingly, let's now look at this code in Python. In this case, the sorting algorithm addresses the elements forward. That is, if we are currently at the ith element, then j1 is the next element after the ith. And in this case, we have exactly the same code as in the pseudocode. In this case, you can notice that the indices have already swapped places right here. Here we start from the first to ni, and here we start from the 0th to ni1. Essentially, we take the entire large array trimmed on the right, in this sorting, and here it is trimmed on the left because we are going backward. There must be an element, and here. If the current element is less than the previous one, we swap them. If the previous element is greater than the next one, we swap them. This way we return our array. There are several variations and they all work the same. It really comes down to what is convenient and preferable for each person and what is easier for them. Take any, and accordingly here it is written that the same sorting is already in C++ with forward traversal. That is, of course, if you want to remember this better, I advise you to take it in your language. Look at one of the sorts, for example, how it works forward, and for practice write a sort that works backward so you don't mix up everything by index. And thus the algorithm is written in C++. It is also called bubble sort, camel case notation, and accordingly we have two loops, if and swap. Basically nothing else is needed here. So that's all for today's lecture. Thank you everyone. Join us for the next lectures and videos.
Want to become a great programmer? Subscribe to our Telegram channel.